Okay, so I hope the slide is also visible.
Yes, sir.
Okay, so thank you, and welcome all to the second session of day 4. So before going into the session, I would like to thank AICT for giving us the opportunity to conduct this FDP, and also I would like to thank the participants for registering and joining for this particular FDP. One instruction for the session coordinators. I cannot see the chat box, so if there is any questions or any questions in the chat box in between, so please forward it to me. This session we'll talk about nonlinear programming. So actually, this session was initially planned to be in the first day or in the second day, because this gives an introduction to one of the key tool that is required for smart grids. So when we talk about smart, we have heard that. So if somebody is smart, that means that he is intelligent, or he or she is intelligent, or he or she can think rationally and take some best decisions. Okay, so the framework to analyze such cases is by something called as nonlinear programming, or in a much common and normal language, it is actually optimization. So in this session, I'm not going into too much heavy technical side, because every session is too much technical. So this session will be mostly of a flavor of a tutorial flavor. So what we'll be doing is we will understand some concepts. So these concepts are not very new concepts. These are very old concepts, but it will be good if we could refresh these concepts, and we will understand some of the concepts more clearly through some of the problems solved during the session. Okay, so please feel free to interact, and I'll go slowly and steadily, and I'll try to finish within the time bound. Okay, so let me come to the yeah. So the overview of today's session. So what is the agenda of this particular session is, we will introduce what is nonlinear programming, and so what is the need of nonlinear programming in relation to smart grids. So where is this nonlinear programming coming in smart grids? And then we will move into one of the easiest concept, which is unconstrained optimization. So I have already mentioned this nonlinear programming is a technical term for optimization. So it is basically solving an optimization problem. And one of the basic type of optimization problem, or one of the easiest one to understand, is unconstrained optimization problem. So there we will see how to solve a unconstrained optimization problem. So most of the optimization problem that we come across in smart grids, or in whichever area we are working, the optimization problem that in hand to solve is will have some constraints. So we'll see the constraints and all later. So that will be constrained optimization problem. But in order to solve the constrained optimization problem, we need the understanding of unconstrained optimization problem. So in order to do the constrained optimization problem, we actually require the understanding of unconstrained optimization problem. And in between, I will introduce one of the most celebrated class of optimization problem, called as convex optimization problem. What is a convex optimization problem, and what is that thing which makes convex optimization problem a very significant one that I'll introduce. And another important concept in constrained optimization problem is called as duality. So this duality makes the constrained optimization problem it's not very easy, but comparatively easier to solve. In general, solving a constrained optimization problem is very, very tough. But the concept of duality makes the life of solving constrained optimization problem comparatively easier. And I'll try to provide an algorithm to solve the constraint optimization problem called as a penalty function algorithm. So some of you may be already aware of this algorithm, but I'll try to explain so that it will be helpful for the whole participants. And if time permits, maybe I'll quickly see an example of game theory, which is actually a forefather of optimization. So we can say, so I'll tell this right now here. So we can say that optimization is actually a particular case of game theory. Okay, so I'll write here if I am not able to get into this section because of time constraint. You just understand this one thing, that optimization is nothing but actually a single player game. So yesterday, Dr. Angur Kulkarni has introduced about games, and you have seen that there are many players in a game. And if we reduce the number of players into a single player, that particular game becomes an optimization problem. Okay. So if time permits, we will quickly look at what is game theory and what is the application of game theory in using a real life example. Okay, so I hope the agenda for today's session is clear. Now we'll move to nonlinear programming. So in my slides there is nothing. It is clean slate. So I'll use the normal whiteboard teaching method so that you can follow along with me. So what is nonlinear programming? So I have already introduced the term, and so it is basically an optimization problem. So optimization problems are generally referred to as, so optimization problems are called as mathematical programming. So it is called as mathematical program. So we have computer programs. So we know that the C language, C++ language. So those are computer programs. But if you say something is a mathematical program, that is actually referring to an optimization formulation. So nonlinear programming is a class of mathematical program where you have the nonlinear functions and so on. Okay, so don't get frightened by the name nonlinear programming. It is just an optimization problem. Now, where is this optimization problem coming in smart grids? So you can say that almost maybe more than 60% or 75% of the problems in smart grid is actually one of the optimization problem. The reason is that optimization problems are used. So you know this. So optimization problems are used to take better decisions. So optimization problems will help to take better decisions. So we always need to decide on something. So we have a few options before us, and we need to choose a best option among that choices are available. So in that case, we need to go for an optimization. Maybe we can go for an optimization formulation to find the better or best decision. So in the case of smart grids, so we have already seen few optimization problems in the sessions. So I'll just list some of the examples. So some of the examples of optimization problems coming in smart grid is One is the social welfare optimization problem. So in the first session, we have seen this. So social welfare optimization problem. So in this problem, the buyers, there are buyers, there are sellers, and so they will submit the bid, and using the bids of sellers and buyers, the system operator will run a social welfare maximization problem, subject to constraints that we need to meet the network constraints, generation limits, and so on. So there the system operator is actually running a social welfare optimization problem to find the solution. Similarly, you have heard about home energy management system. So home energy management system. If you want to manage the energy distribution in home, for example, if you have a solar cell, if you have battery, if you have electric hybrid, plug-in hybrid electric vehicle, how to choose. So there are in these cases we need to take some decisions, and the reason for optimization coming into the play is that we have a lot of decisions are available. We can take any of those decisions, and which is the best decision is what we need to understand. So we have battery scheduling problem in home energy management system. So almost every problem we can frame it as an optimization problem. So the challenge involved is how to frame the given problem. So if you have a problem to solve, how to frame that problem as an optimization problem is the key challenge. Okay, so now coming to little more details of nonlinear programming or optimization problem. So in an optimization problem, you basically need three quantities. So at least these three quantities are required in an optimization problem. So the three quantities required in an optimization problem are, one is the feasible set. So I'll go a little slow. One is the feasible set. So it is actually the set. So I'll represent it as capital X. It is a set which contains the set of actions, set of possible actions. Okay. So I can either select one action, or I can select another action, and so on. So it is a set of all collection of all the actions. Second thing is what we need to define is we need to define an objective function for each element in the feasible set. Okay, so we need to define an objective function. So this objective function is defined for each element in the set. So it is a function which is a mapping from capital X, which is the feasible set, to an R. So if there are 5 elements in the feasible set, for example, if this set has 5 elements, say x1, x2, x3, x4, and x5, I am considering a case. If this feasible set has 5 options, and for each option, what is the value which is assigned to each option is what is this objective function 6. For example, for action 1, you have a value say 4. For action 2, you have a value 2. For action 3, you have 1. Maybe for this you have 6. This you may have 9. Okay. So this is actually this function. What is the mapping of each element in a feasible set to a real number? So you need to have a feasible set. What are the possible actions that are available, and what is the function which is mapping the possible actions to a real number? And third thing is you require a decision variable. So this is a variable which belongs to the feasible set. So these are decision variables. So let me represent it as X, which belongs to the set capital X. So at least these 3 things are required. So there are more things that we can add to it. For example, we can add constraints and so on. So I'm not adding that for the moment. I'll try to keep it as simple for the moment. So at least these 3 things are required for an optimization problem. And if we have these 3 things, we can write the optimization problem either to maximize or minimize. So sometimes we need to maximize some functions, or sometimes we need to minimize some functions. So, so as a general case, I'll consider minimizing problem. So we need to minimize the objective function f, and f is a function of the decision variable x, because f is a mapping from capital X to R, and this decision variable belongs to this capital X. So minimize the function, objective function f with the variable x, and we generally write the decision variable below this minimization like this, subject to the decision variable belongs to the feasible set. The feasible set is also called as constraint set. So this is the fundamental way of writing an optimization problem. So I hope almost every one of you is familiar with this framework. So if you can write any problem in this particular form, then you can call that problem as a mathematical program. Okay. So any problem in this particular formulation is actually a mathematical program. And what is nonlinear programming? So nonlinear programming is the most general case. It is the most general case where this f, the function f, is nonlinear. So f can be linear, f can be nonlinear. So nonlinear is the most general case. And if f is nonlinear, and if this set x so I haven't put any restrictions on the feasible set x. Okay. So in general case, the problem at hand is actually what is called as nonlinear programming problem. So you cannot have something which is more general than this. So if you have a theory for nonlinear programming problem, that theory can be applied to any optimization problem. So later we will add some restrictions to this f. For example, we require this f to be continuous, f to be differentiable, and so on. So that we will add later. But for the moment, nonlinear programming is any programming problem with this particular structure, with f being the objective function, x being the decision variable, and capital X being the feasible set. So I hope this much is very clear and is already known to you. So can I get a feedback from any participant? So is that clear?
Yes, sir. It is clear.
Okay, fine. Thank you. So now let me quickly go into what is the solution to this problem. So if that is an optimization problem, so always have this particular framework in your mind throughout this session. Okay, so we want to minimize f of x subject to x belongs to capital X. Now what can be thought of as a solution? So a solution can be thought of as one of the variable, one of the decision variable x star, which actually belongs to capital X, the constraint set. And what is the property that this x star need to meet? The property that x star need to meet is that particular x star must minimize the objective function. So that x star must be less than f of x for all x belongs to the set. So this is denoting for all. So if you consider all decisions in the all elements in the constraint set, and if x star is giving me the least, then that is actually the solution. So this is actually the solution, which is called as global minimum. So we'll come to local minimum later. So here I am considering the whole set of feasible set or constraint set, and in that, if x star is minimizing, if you take all set, then that is actually the global minimum. So just for notational representation, because in paper, if you read journal papers and conference papers, you have these notations keep on repeating. So I just want to make sure that these notations are clear to you. So this x star this X star is called as is the optimal solution or the global solution. So this X star is the optimal solution, and f of X star. So these are two different things. So if you have an optimization problem, and if you have X star, which is the optimal solution, and f of X star is the value of the objective function at that particular optimal solution. So this f of X star is called as optimal objective. So this is the optimal objective. And hence we can write, so f of X star is actually, so in a neater way, I can write f of X star is actually minimize f of X, and sometimes I'll write like this as well, X element of X. So I'm avoiding subject to and so on. Okay, so in a neater way, I can write f of X star as actually like this. It is minimization of f of X with X subject to capital X. And X star is written as argument of this. So argument of minimization of f of X with X belonging to capital X. Okay, so these are two different things. Sometimes we tend to confuse between f of X star and X star. So X star is actually the optimal solution, and f of X star is the optimal objective function. Fine. So far it is very basic, very fundamental. Now we will move quickly into unconstrained optimization problem. So what is an unconstrained optimization problem? So if you see the previous problem that I have written, we have a constraint actually. I haven't mentioned about constraint, but we actually had a constraint, and the constraint is that we have the set X. So this X, small x, can belong only to the set capital X. So this is actually a constraint. So this capital X is actually a constraint set, and this is actually a constraint. So in the case of unconstrained optimization problem, we have there is no constraint on the optimization problem, or you can say this capital X is actually the whole Euclidean space. Okay, R raised to n. Okay, so this is very basics of unconstrained optimization problem, or you can write an unconstrained optimization problem as minimize f of X with X belonging to R raised to n. Okay, so where n is the number of variables in this decision variable. Okay, so let's quickly consider an example. So as I said, this will be a tutorial session. We'll consider a lot of examples to understand each and every minor concepts. So let's consider the case when n is equal to 2. So it is very easy to visualize. So n is equal to 2 means there are two axes, and so we can take the function f, which is so here a capital X is equal to r square. So f is a mapping from r square to r, and let's consider such a function. So let's consider f of x comma y, and let the function be as an example. Let's consider x into e raised to minus x square minus y square. Okay, so this is actually a function in two-dimensional space, and I am not putting any constraint on the on this objective function. Okay, so there are two variables. One variable is x, another variable is y, and these two variables are coming in this objective function. Now the solution. So how to find the solution? So we can write this problem just to make it clear. So we can write this problem as minimize x e raised to minus x square minus y square, and the decision variables here are x, y, which belongs to R2. So this is the optimization problem we are trying to solve. Now, how to solve this problem? Can anybody help me with the method to solve this problem? Suppose you are given with this problem. So I am pretty sure that most of the participants know these things, but as I said, we'll quickly jump into constraint optimization problem, which may not be familiar to many participants, but this I am pretty sure that you are familiar with. So can can any one of the participants help me to understand how to solve this problem? So how to find the optimal value and how to find the optimal objective function? Anybody?
Partial differentiation.
Partial differentiation, you are correct. So how to find using partial differentiation? So you have this function. So what should I do?
Differentiate with respect to x and then with respect to y.
Very good, very good. So differentiate. So I'll write. So differentiate with respect to x. So differentiate with respect to x and y. Okay, then
Equate both the derivatives to 0.
very good. So differentiate with respect to this and equate to 0. So with that, will we get the solution?
That could be maximum or minimum.
Very good. So that could be maximum or minimum.
So we have to take the second derivative.
Then it's not clear, sorry.
We have to take the second derivative.
Okay, so you need to take this as a second step. You need to take the second derivatives, and
if that is positive, then it's a minimum.
okay, second derivative, if it is greater than 0, then that point will be minimum. And otherwise, if it is less than 0, that point will be
maximum.
Thank you very much. Who is that person? Just to know the name.
Krishna Rao.
Sorry?
Krishna Rao.
Okay. Thank you, sir. Okay, so this is how we will solve the problem. So in order to make it more concrete, I'll try to explain it once again. So this problem can be solved actually using two conditions. One condition is called as necessary condition, and second condition is called as sufficient condition. So this is what sir has helped me to write these. So these two conditions. So what is this necessary condition? So what necessary condition is saying is that if somebody has given me a point and saying that particular point is the solution, and then that point need to satisfy the necessary condition. So I'll write it here so that it will be clear. So if somebody say x star is a solution, if x star is a optimal solution to the problem, then this x star must satisfy the necessary condition. Okay. So if somebody say an x star is a solution and that particular point is not satisfying the necessary condition for solution, then that point is not a solution. Okay. So if x star is a solution, then that x star must satisfy the necessary condition. In this unconstrained optimization problem, the necessary condition is actually the gradient, the first derivative, gradient of f. So gradient is actually taking the derivative with respect to x as well as y in this particular case. So the gradient of f need to be equal to 0. So this is the necessary condition in the case of unconstrained optimization problem. That means if somebody gives a solution and I'll check whether the gradient is 0 at that particular point, if that is satisfied, I can say that that could be, it is not necessary that is a minimum, that could be maximum as well, but it must satisfy the necessary condition. Now coming to sufficient condition, what is sufficient condition is saying is that, so can somebody help me what is sufficient condition similar to this? So necessary condition is if x star is a solution, then that must satisfy a necessary condition. Similarly, what could be so what can be a sufficient condition? So sufficient condition says that if x star satisfies sufficient condition. So if x star satisfies sufficient condition, then then X star is a solution. Yeah, so sufficient condition says that if a set of condition is satisfied by a particular point, then that particular point is a solution. So the sufficient condition in this particular case is actually the sufficient condition is that there are two conditions. First condition is that the gradient need to be 0, and the Hessian, which is actually the second derivative, with second derivative. So this is actually Hessian. Hessian need to be, can anybody help me with this? So this is actually need to be
Negative.
No, we are talking about minimization problem.
Positive.
So Hessian need to be
Positive.
yeah, it's not positive, it's actually positive definite. The reason is that here we are talking about matrices.
Okay.
So in matrices, we don't have, it's not a scalar. We have matrices. So if you have a matrix, we cannot say whether it is positive or negative, but we need to say in terms of definiteness, whether it is positive, definite, negative, definite, positive, semi-definite, negative, semi-definite, and so on. So in general case, we need the Hessian to be positive, definite, and at the same time, the gradient to be 0. Okay. So this is the necessary condition and the sufficient condition for unconstrained optimization problem. Now I'll add one more point to this. Necessary conditions are not sufficient and sufficient conditions are not necessary. Okay, so I'll tell it slowly. What I'm saying is necessary conditions are not sufficient and sufficient conditions are not necessary. So what I meant is that these conditions will not tell that X star is X star or if a point satisfies this condition, then that point need not be a minimum. That is very clear, because a maximum point also can satisfy this point. But the other thing is may not be that clear. So is these conditions necessary? What I am saying is, if these conditions are necessary, what it means is that if somebody says that X star, Y star is a solution, then that point must satisfy these conditions. So is that always true? If X star, Y star is a solution, will it always satisfy this particular condition? This is true in this particular case, but that is not always the case. Okay, so I'll just give a counter example. If f of x is if f of x equal to, so this is another example. If f of x equal to x raised to 4, okay, let's say so this f is a mapping from R to R, a very simple one. Okay, so what could be the minimum of this problem? Anybody? What is the minimum of this problem, f of x equal to x raised to 4? So this function will look something like this. It is actually a more steeper function like this. This is f of x, this is x. So what is the minimum of, what is the optimal solution to this problem?
Origin.
It is actually?
Origin.
Yes, origin, or it is 0, right? But so I am saying that x star equal to 0 is a solution to this problem. If these are sufficient, if these are necessary condition, then it must satisfy these conditions. But we can see that this condition is not satisfied, right? Why this condition is not satisfied? Because if you take the second derivative, so if you take the first derivative, it is 4 x cube equal to 0. So when x equal to 0, that becomes 0. That is fine. Now if you take the second derivative, it becomes 12 x square. And that also becomes 0. Yeah. But we require that to be greater than 0. Okay? It is not greater than or equal to 0. We require that to be greater than 0. So what I am saying is that sufficient conditions are not necessary and necessary conditions are not sufficient. Okay. So I hope so far it is clear to you. Now what I'll try to do is I'll try to demonstrate this particular example. So this particular question, in order to get a better feel of what is this necessary condition and sufficient condition, I'll try to demonstrate with the help of Matlab. I'll just try to plot that particular graph. So can you see the Matlab window that I have opened?
Yes, sir.
Okay, fine. So this is a very straightforward, I mean, easy command lines that I have written. So I have defined the axis in this step. So I have defined x-axis, which is varying from -3 to 3. So basically, I am interested in that region. And I have defined a mesh grid using a Matlab. And here I have defined that particular objective function. So objective function is equal to x into e raised to minus x square minus y square. So is that the, yeah, x into e raised to minus x square minus y square. And now I am just trying to plot that using the command mesh. So I'll just evaluate this much so that you can see what is that function. Okay, so you can see that this is the function that we have defined, and by looking at that function, so we can see the function. You can see that it has so the first derivative will be satisfied at least at 2 points. Okay, so this will be a point where the first derivative, I mean the necessary condition, is satisfied, and this is the another point where the necessary condition is satisfied, and the sufficient condition will be only satisfied at this particular point. So even though this function has both maximum and minimum, we require the necessary and the sufficient condition to identify the maximum as well as the minimum. Okay, so one more thing I want to demonstrate in Matlab is so this is actually the plot of the function. Now, if you want to see more clearly of where is the maximization and minimization happening, we need to take the contours of this plot. So what it means about contour is, if you are cutting this graph at some height, suppose I am cutting the graph at say 0.1. Okay, so if I am cutting the graph at 0.1, you will get a circle, right? A circle something like this. And if you cut it at minus 0.4, you will get a similar circle, but with a reduced radius. Okay, so if we have contours, we can clearly identify whether it is a maximization or a minimization which is happening for this function. So in order to do that, I have defined the contour as well. So I'll just try to tell this. So there we'll see both function as well as the contour. Okay. So figure 1 is the function which I have already shown, and figure 2 is the contour. So what contour says is that if we are cutting at certain points, what is the value at those points is what is written in circles. Okay, so here I have a circle which is cut at 0.35. So this number of circles we can define. So I have defined it as some 10 points, something like that. Yeah. So here I have defined the number of cuts or number of levels that I require is 10. That's why we have 10 circles like this. So what I was trying to say is, from this we can see that a function is maximizing in one direction and a function is minimizing in another direction. And the area where it is maximizing is actually is given by this side, because yeah, so you can see that sorry, so which side will be maximizing and which side will be minimizing? Can you help me in that? Is right side maximizing or left side maximizing?
Right side maximizing.
Right side is maximizing. Yeah, correct. So it is increasing in this direction, and the left side is minimizing. Correct. So using this contour plot, we can actually find. So this is actually getting into a point somewhere here, and this is actually getting into a point somewhere here, and we can use the first derivative to get the maximizing the point, it could be maximum or minimum, and maybe we can use this contour plot to identify which is the maximum or minimum. Okay, so that is how we can graphically view the things, what is happening in unconstrained optimization problem. Fine. So now, yeah. So we have seen about global minimum. Now I just want to introduce about local minimum as well. So if you have a function, so I'll try to draw a one-dimensional function. So here you have x. So since it is a one-dimensional, you only have f of x. And let's consider a function something like this. Something like this. Okay, so if you take the first derivative of this function, you will observe these points. So if you take the first derivative, you will get this point, and if you take the first derivative, you will get this point, and even this point also you will obtain, even this point you will obtain, and even you will obtain this point as well. So here also the first derivative becomes 0. If there is a flat point, all those points you will obtain this point as well. Okay, so by taking the first derivative, you'll get these points. So I'll not denote this as maybe x1 and x2. So these are minimums, right? So this is a minimum, and this is also a minimum. So if you take the first derivative, that means df by dx equal to 0, the solution of this will give me x1 as well as x2, and there will be other solution as well. So for the moment I am not considering the other solutions. Now how to check which is the minimum? So what you need to do is you need to take the second derivative, d square f by dx square, and you plug in x1. So you check for x1, and what will be this value? This value will be greater than 0. And next you will check for this value, d square f by dx square at x2. What will be this value? This value will be always, this value is also greater than 0. Okay, so these 2 points are minima. So using necessary conditions and sufficient conditions, what I am trying to say is sometimes it is difficult to identify or difficult to distinguish between local minima and global minima. So you can see that this is actually x2 is a global minima. So this is the global minimum, which is what I require as a solution. But sometimes this person, the local minima, also may try to mistakenly represent as global minima. So this problem is a big problem in optimization actually. How to differentiate a local minima and global minima? In many a times, what happens is we will try. So it's about algorithms in optimization. In any algorithm, we need to start with an initial guess. Sometimes we'll take the initial guess as, for example, if you take this as the initial guess, the algorithm will take me to the local minimum, and it will say that this is the minimum of the problem. But it may not be the solution. There exists a global minimum which may not be identified. Okay, so at the same time, if you started at somewhere over here, it may get me to the global minimum, and it's difficult to identify whether I have reached the global minimum or not. So this local minimum has created a lot of problems in finding the solution of an optimization problem. So one of the solution to get rid of the problem of local minima is actually what is called as convex optimization problem. So in the case of convex optimization problem, the key highlight is that there is no problem of local minima. Okay, so I have said that if there is a local minima, there is a tendency that the algorithms may converge to that local minima and pretend to say that that is the global minima, but that need not be the global minima. But for convex optimization problem, there is no such problem of local minima. The reason is that every local minima will be a global minima. So the reason is that in the case of convex optimization problem, every local minima will be a global minima. So you don't need to worry whether it is a local minima or a global minima. If you have reached a solution, you can straight away say that that is actually a global minima. So that is the significance of convex optimization problem. So there are other significance as well, but this is one of the key factor why convex optimization problem is so much popular. Now, what is this convex optimization problem? With the formulation that we have discussed, it is very easy. So the formulation that we have discussed is minimize the objective function f of x subject to, so x being the decision variable, subject to x belongs to the set capital X. So in the case of convex optimization problem, now I am adding few constraints to this problem. Even though it is a nonlinear programming problem, I am putting additional constraints to this optimization problem so that I don't need to worry about the local minimum. So the constraint is that we require the objective function f to be a convex function. So I'll introduce in a minute what is this convex function, and the constraint set x, capital X, this need to be a convex set. So if you are given with a problem with this f being convex function and this capital X being a convex set, then you can call that problem as a convex optimization problem. And for that particular problem, if you have a minima, then that minima will be global minima as well. And many of the optimization problems, for example, linear programming problem. So linear programming problem is actually a convex optimization problem. Even quadratic program. So quadratic program is where the objective function is quadratic, and the constraints that are affine and so on. So that is an example of a convex optimization problem. And so there are a lot of cases of convex optimization problem, and in convex optimization problem there is no problem of local minima. Now, what is this convex function and what is this convex set? I'll quickly introduce and I'll move further. So this convex set, so I'll tell what is this convex set. So these concepts also may be known to some of you, but this may be new to some of the participants. So for those who are new to this concept, I'll try to explain it little slowly. So this convex set, so this set X, so this set X is a convex set. So this set is a convex set if it satisfies the following property. So if for any x, y that belongs to the set capital X, and if you consider a scalar lambda between 0 and 1, we require the condition that lambda x plus 1 minus lambda y belongs to the set X. So this is the definition of convex set. So what it says is that if you have a set, so I'll try to demonstrate it in the case of two-dimensional so that it is easier to understand, which can be easily extended to any dimension. So if you have a two-dimensional set, and if you are defining a space something like this, or a set something like this, okay, this set is convex if it satisfies this condition. And what this condition is saying is that you consider any 2 point in the set xy, in the set x. So this is capital X, and you consider any 2 point in the set. For example, I am considering this point as x, and I am considering another point here. Okay, so you can consider any point. It can be in the boundary, but not outside the boundary. It's outside the boundary is not a part of the set. So if you consider any 2 points like this, okay, and now you try to understand what is this lambda x plus 1 minus lambda y, where lambda is varying from 0 to 1. So if lambda equal to 0, let's consider the case when lambda equal to 0. So if lambda equal to 0, you can see that lambda becomes 0. So this becomes, the first term becomes 0. And if lambda equal to 0, it corresponds to the point y, right? Because 1 minus lambda is 1. So this corresponds to the point lambda equal to 0. And if lambda equal to 1, it becomes 1x plus 0y, and this corresponds to the point x. So lambda equal to 1 corresponds to this point. So now this lambda takes a value between 0 and 1. So for lambda equal to 0, it corresponds to the point y. For lambda equal to 1, it corresponds to point x. And now the lambda is varying between 0 and 1. That means it can take any value in between. So if you take lambda equal to 0.5, it will be this point, which is actually midway between x and y. If you take 0.1, it will be some other point. Okay, so it is actually a straight line which is connecting x and y. So is that clear to the participants? Anyone can respond? So I'm asking question in between so that I can make sure that I am also connected. You are listening to me. You are listening as well. So is that clear? What is happening with this function?
Yes.
Okay. Thank you.
Yes, Matthew.
Okay. Fine. So this is actually a straight line connecting x and y, and as I said, x and y can be any 2 points in this set. And if this is true for any 2 points in the set, then you can call that set as a convex set. For example, if you take, I am taking this point and this point, and I am drawing a line between these 2 points, and these 2 points are an element of the set itself. All the points in this line are an element of this set, and if you take any 2 points, that is the case. Okay, so if that is the case, then that set is called as a convex set. I'll give an example of a non-convex set. So if you have a 2-dimensional case where, for example, if you have something like this is not an example of a convex set. The reason is, if you take any 2 points like this, so suppose I am taking a point here and a point here, and I am drawing a line between this, all those points are inside, so that is satisfied. But this is not satisfied for a point here and here. Suppose I am taking a point x here, I'm taking a point y here. And if I am trying to draw a line between x and y, you can see that these points are outside the set. Okay, so this set x is not a convex set. So this is the basic definition of a convex set. And for convex optimization problem, we require the set to be a convex set. Now let me quickly explain what is a convex function. So a convex function, it has a similar definition. So a convex function. So since it is a function, it is a mapping from x to r. And for convex function, we have already said that we require this x to be a convex set. And this function f is convex if it satisfies this property. So I'll write the property. So for any x, y belongs to the set x, and for any lambda belongs to 0 and 1, so this is you have already seen in the convex set case. Now I am defining for convex function. A function f to be convex if f of lambda x plus 1 minus lambda y. So when you see this, you need to understand that it is actually a straight line between x and y, because lambda is varying from 0 to 1. This need to be less than or equal to lambda f of x plus 1 minus lambda f of y. So if a function satisfies this property for any x, y belongs to the convex set, and the scalar lambda varying from 0 to 1, then you can say that function is an objective function. Sorry, that function is a convex function. So, so what does this mean? This part is actually saying a line between x and y. What does this mean? This is actually a line between f of x and f of y. So I'll try to demonstrate with a figure, so it will be more clear for you. So I'll consider the one-dimensional case, and this can be extended to any dimension. So here x is the decision variable, and f of x is the objective function, and this objective function need to be convex. That means it has some shape, something like this. And let's consider 2 points, any 2 points, and let's consider the convex set. So for example, this is the set X, and is this set convex? This set is convex. The reason is, if you take any 2 points in the set and draw a line between these 2 points, and all those points are within the set. For example, if I take this X and if I take this as Y, by the definition of convex set, if you draw a line between X and Y, and if all the points in that line are in the set, then that set is a convex set. So this set can be thought of as, this set X can be thought of as a convex set, and hence the mapping is fine. Now I am considering the point in the function. So this point is actually, this point is f of x, and this point, so here I am drawing a straight line, so this point is actually f of y. Okay, now we will check this definition. So what this definition is saying, now I will first see the right hand side. What is the right hand side saying? The right hand side saying is, you need to draw a line between f of x and f of y, because when lambda equal to 0, it corresponds to f of y, and when lambda equal to 1, it corresponds to f of x, and for any value between lambda between 0 and 1, you have the points between f of y and f of x. So this right hand side is actually a straight line connecting f of x and f of y. Okay, so this is the right hand side, this is RHS. And now what is this left hand side? Left hand side is saying the function value with the arguments being the straight line between x and y. So if you have x and y, lambda x plus 1 minus lambda y corresponds to this region. And at all these regions, what is the function value? So what is the function value at all these regions? The function value at all these regions is actually these, the one represented in green. Okay, and what you require is, this function value must be always less than or equal to this straight line connecting f of x and f of y. And that need to be true for any x and y. If you consider any x and y in the region, in the convex set, if this condition is true, then you can say that that particular function is a convex function. Okay, so I was trying to explain, explain slowly what is the definition of a convex function, and how to check if the given function is a convex function. So just to recap what we have discussed, if you draw any line between any 2 points, if the function is below that line, then that particular function is a convex function. So so from this case, you can clearly see that there is no problem of local minima. If the function is a convex function, every local minima will be a global minima. I'll give another example of a convex function. So if you have a function something like this, so I'm drawing something like this. So this is also a convex function, but here you have multiple local minima. I mean multiple minimas, global minima as well. Okay, so this is also a convex function. The reason is if you draw a line between any 2 points, the function value is below that line in this case as well. Now there is a concept called as strictly convex function. So here in this case there are multiple minima, and in the case of strictly convex function, so I'll just add here so that I can save some time. Strictly convex function. For strictly convex function, there will be unique minimum. Okay, so in the case of convex function, there can be more than one minima, but for a strictly convex function, you can have only one minima, and the change that you require is you need this to be just less than, left side need to be less than this, and there is one more change, this lambda need to be between open interval 0 to 1. So I'm not taking time to explain this, but you can refer standard optimization textbooks to understand this strictly convex function. So this strictly convex function can only take this form, and it will have only a unique minimum. Okay, so that is about convex optimization problem, and the good part is that for convex optimization problem, you don't need to worry about the global minima, because every minima will be a local and global minima. Now let me quickly come to the constrained optimization problem. What is a constrained optimization problem, which is the most general case, and what is the first order necessary condition for solution of an optimization problem. So let me add one more thing in the case of convex optimization problem. I have mentioned that in the unconstrained optimization problem, we have necessary condition as well as sufficient condition. And if you remember, the necessary condition is actually first order condition, and sufficient condition includes the second order, I mean the second derivative condition. For a convex optimization problem, this is very important. I forgot to mention. I'll write here. For a convex optimization problem, the first order necessary conditions are sufficient. So during while introducing the unconstrained optimization problem, I have mentioned that the necessary conditions are not sufficient. So that is very evident. But for convex optimization problem, this is the power of convex optimization problem. You just need the first order necessary condition to find the solution of the convex optimization problem. That means if you have a convex optimization problem and you find for an unconstrained optimization problem, you take the derivative, I mean the gradient with respect to the decision variable and equate to that 0. Whatever you are getting as the solution to this problem, that will be the solution of the convex optimization problem. You don't need to check the second derivative. Okay, so that is the power of convex optimization problem. Fine. So now we will quickly move into the constrained optimization problem. So why I told about convex optimization problem is in constrained optimization problem also we have the first order necessary condition as well as second order necessary condition. And if the problem at hand is a convex optimization problem, you just need to check the first order necessary conditions, because as I said, for convex optimization problem, the first order necessary conditions are sufficient. You just need to check the first order necessary conditions to find the solution of a constrained optimization problem. Okay, so I'll quickly go through the first order necessary condition of, first I'll define the constrained optimization problem, and I'll try to explain the first order necessary condition in constrained optimization problem. I may not get the time to discuss the second order sufficient conditions, so we'll restrict our analysis to convex optimization problems so that the first order necessary conditions are necessary and sufficient. So what is a constrained optimization problem? So the problem formulation is almost the same. we have minimized the objective function f of x and x being the decision variable. Now we have the constraints. So I'll try to elaborate the constraints. Previously I have written as small x belongs to capital X, which is the constraint set. Now I'll try to elaborate what is that constraint. So the constraints can either be an inequality constraints or it can be an equality constraint. So I'll write the equality constraint first. So it may be represented as ei of x. So since it is an equality constraint, this is equal to 0. And there can be any number of equality constraints. So I can be varied from 1 to, for example, say m. Okay, so there can be m equality constraints and there can be inequality constraints. So as a general case, I'll write it as less than or equal to. So even if you have a problem with greater than or equal to constraints, you can easily convert that into a less than or equal to 0 problem. So the inequality constraints can be of any number. So I'll write it as j is equal to 1 to L. Okay, so this is actually the general case of constraint optimization problem. Just to connect it to the previously defined formulation, what is this x here? So this x is defined as those x's, x belongs to Rn such that which satisfies these two set of conditions. It includes the equality constraint as well as the inequality constraint. So the constraint set x, capital X, is those x's which satisfy the equality constraints ei of x equal to 0 for I varying from 1 to m and hj of x less than or equal to for j varying from 1 to L. So this is actually the x that we have defined previously. Now, what is the necessary condition? Remember that the necessary condition in the case of unconstrained optimization problem, so the necessary condition in unconstrained optimization problem was that the gradient of the function need to be equal to 0. In the case of constrained optimization problem, we need to define something called as Lagrangian function. So for a constraint optimization problem, we need to define something called as Lagrange function. And just to understand quickly, we require the gradient of this Lagrangian need to be equal to 0. So this is a big, it's a general case, but I'll come into the specific details later. Instead of this function f, we have a Lagrangian function, and the first order necessary condition says that the gradient of Lagrangian function need to be 0. So what is this Lagrangian function? So in order to define Lagrangian function, we need to define something called as Lagrange multipliers. So for each of the equality constraints and inequality constraints, we will define a multiplier. So let me define a multiplier for equality constraints as a mu I. So there are m number of mu i's, and the Lagrange multiplier corresponds to inequality constraints as lambda j. So these are actually Lagrange multipliers. And we will use these Lagrange multipliers to define the Lagrange function. So now what I am going to define is Lagrange function. So Lagrange function is defined as, so it has the variable x, which is the decision variable, and the additional variables are the Lagrange multipliers. These two variables are also there. So we have x, mu, as well as lambda, and this Lagrange function is actually the objective function plus the Lagrange multiplier times these constraints. It's very easy. It is this objective function f of x plus Lagrange multiplier times these functions. So I'll quickly write what is Lagrange function. It is f of x plus, now we consider the equality constraints. So it is mu I times ei of x. So these are equality constraints. So there are m numbers. So we need the summation. Summation I is equal to 1 to m plus lambda j lambda j hj of x. So these are these corresponds to the inequality constraints, and lambda j's are the Lagrange multipliers corresponding to the inequality constraints. And we have L number, so j is equal to 1 to L. Okay, so this is the Lagrange function. And so I'll just repeat it once again. If we have a constraint optimization problem, we must write it in the standard form. So this is actually the standard form. We need to write it in the standard form. We need to define the Lagrange multipliers for each constraints. And once we have the Lagrange multipliers, we need to define the Lagrange function using the Lagrange multipliers. Once we have the Lagrange function, the first order necessary condition is that, so I'll write first order necessary condition. And these conditions are sufficient for convex optimization problem, but not sufficient for general case. And these first order necessary conditions are very popularly called as KKT conditions. So if you look at any paper, any journal paper or conference paper, research paper, which involves optimization problem, you cannot write that paper without mentioning this name. Okay, so that much important is this first order necessary condition. So this condition is called as KKT condition. So KKT is actually the name of scientist Karush Kuntakar. So these are actually three people who put forward these necessary conditions. So this KKT condition says that, so the first condition, so there are actually three conditions. I'll first put the numbers. The first condition I have already mentioned. First condition is that the gradient of the Lagrangian need to be equal to 0. So lambda, so L is the Lagrange function. If you take the gradient with respect to x, and that need to be equal to 0. Similar to the objective function to be 0 in the case of unconstrained case, here we have the gradient of Lagrangian to be 0. So that is the first and primary condition. The second condition is what is called as complementary slackness. The second condition is called as complementary slackness condition. And what it says is that the product of Lagrange multiplier times Hj need to be equal to 0. So lambda j times Hj of x need to be equal to 0, and that need to be true for all j's, j equal to 1 to L. And third condition is that this lambda j must be non-negative, must be greater than or equal to 0 for j equal to 1 to L. Okay, so these three conditions are what forms the KKT conditions. And for a solution of constraint optimization problem, if x star, for example, if somebody say that x star is a solution, we need to find an equivalent, we need to find a appropriate mu star and lambda star, which are Lagrange multipliers, such that it satisfies these three conditions. If that is the case, if it is a convex optimization problem, we can straight away say that that is a solution to the problem. If it is not a convex optimization problem, we cannot directly say that is a solution, but that could be a solution. In that case, we may need to go for the second order sufficient conditions to confirm it whether that particular point is a solution or not. Okay, so I thought of doing a sample problem, but because of time constraint, I am not taking time to solve a problem. I'll just quickly go into the next thing, which is duality. What is duality? So if you understood what is Lagrange multipliers, these Lagrange multipliers are called as dual variables. Okay, so I'll write it here itself. So so the problem, the decision variable x is called as primal variable, and the Lagrange multipliers lambda and mu, these are called as dual variable. So I'll quickly explain what is this duality in optimization problem, and maybe we'll stop with that. We may not get time to explain penalty function. Fine. So what is duality? What duality is saying is that it is actually posing a question. So the question is that solving this this constrained optimization problem, even with first order necessary conditions, it's not easy. So if you try to solve this particular problem using first order necessary conditions, you will have a lot of conditions because of this condition. If lambda is greater than 0, lambda equal to 0, and depending upon the number of inequality constraints, you will have a lot of conditions, and it's not at all easy to solve a general constrained optimization problem. Okay, it's not at all easy to solve a constrained optimization problem. So the question that we are asking is there an easier way to solve the problem? Is there an easier way to solve constrained optimization problem? The answer is yes, and the answer is actually dual problem. Why the dual problem is easier to solve? The reason is, this is very, very important. The reason is that dual problem will be, I am stressing, will be convex. Dual problem will be always a convex problem, even if, so the initial problem is called as primal problem, okay? Even if the primal problem is not convex. This is very, very powerful thing in optimization. Okay, so the dual problem, if you formulate a dual problem of the given primal problem, that will be always convex. So I'll write that as well. That will be always convex. There is no doubt in that. What is the advantage of convex programming problem? If you have a convex programming problem, then you need the first order necessary condition to solve the problem. Okay, so the dual problem will be always a convex problem, and even if the primal problem is not convex, and hence the dual problem can be used to solve the primal problem. But the problem is you may not always get the exact solution. What we require is the exact solution of the primal problem, but by solving the dual problem, we may not get the exact solution, but we will get a solution somewhere near to the exact solution. Or we can say that we can give a bound on the solution of the primal problem by solving the dual problem. Okay, but in some cases, the dual problem, the solution of the dual problem is actually the solution of the primal problem as well. In any case, the dual problem is always convex, and hence we can find the solution of a dual problem. Now let me quickly tell you what is a dual problem. So the dual problem is actually defined using a Lagrange function. So first let me write the Lagrange function once again. So Lagrange function is L mu comma lambda, which is actually a function, objective function plus summation mu e. So I'm not writing the other variables for the moment. So you can fill that later. So this is the Lagrange function that we have defined, right? Now, what is a dual problem? So in order to define a dual problem, the objective function of dual problem is actually denoted by, maybe I'll write it as theta, and it is in the space of dual variables. So I have mentioned that lambda and mu are called as dual variables. So the primal problem, which is the problem that I need to solve, it is in the space of x. Now I have a dual problem which is in the space of dual variables, and the objective function of the dual problem is given by theta of mu and lambda, which is nothing but it is actually a minimization of L of x comma lambda comma mu. Yeah, so it is actually an unconstrained optimization problem. So here L is just an objective function, and you just need to minimize with respect to x. What you will obtain is actually this theta, and the dual problem is given by, so I'll write the dual problem. Maybe I'll stop with this. So the dual problem is given by maximization of theta, which is the objective function of the dual problem, with the variables being mu and lambda, the dual variables. So the distant variables in this case is lambda and mu, subject to the condition that we require the lambda, the Lagrange multiplier corresponding to inequality constraints, to be greater than or equal to 0. So this is the dual problem. It look neater, and remember, if there are no inequality constraints, there is no constraint like this as well. And the dual problem is completely an unconstrained optimization problem. Moreover, the dual problem is a convex problem, and hence you can use the first order necessary conditions to find the solution to this problem. And if the solution to this problem is given by, let's say this is d star. Remember, this is optimal dual objective function. Okay, and suppose the solution to the primal problem, suppose this solution is given by p star. Okay, solution to the primal problem is p star, solution to dual problem is d star. Then a duality theorem says that, there is a theorem called as duality theorem. It says that this p star, which is the primal solution of the primal problem, will be always less than or equal to d star. So this is actually weak duality theorem. And there is something called as strong duality theorem, which imposes some constraints on the optimization problem. It says that p star is equal to d star. That means you just need to solve the dual problem to obtain the solution of the primal problem for if strong duality holds. If it is a weak duality, as I said, the dual problem will give a solution which is actually bound to the primal problem. Okay, and the difference between this d star and p star, so d star minus p star, is actually called as a duality gap. This is
Sorry, lower bound or upper bound?
Sorry?
It is lower bound or upper bound?
Yeah, so the question is not clear. Maybe can you repeat?
Lower bound or upper bound?
Okay, so the duality. One second. So p star.
Sorry, you told the solution of your Convex bound to the prime problem.
Yes, I'm sorry. This is reverse actually. Thank you for this correction. So because of by weak duality theorem, this will form the lower bound. The dual solution will form a lower bound to the primal point. So thank you for that correction. Thank you. Okay, so that is about duality. I don't have the time to go into the penalty function and the game theory example also I thought of introducing, but we'll stop here and we'll take some questions So I hope you got an overall picture of what is happening in a nonlinear programming problem. The first order necessary condition is the backbone of constraint optimization problem. You need to define the Lagrange multipliers, Lagrange function, and many times what people will do is they will write the dual problem and try to solve the dual problem and try to relate the solution of dual problem to the primal problem. So with this, I'll stop because it is time. Is there any questions or any comments?
Can you recommend book or course where all these are explained as lucidly as you have done?
Okay, so one of the textbook that I used to refer to study this is actually a book by Amir Beck. This is actually a very good book. I think the name is, I forgot the name, in Introduction to Optimization or something like that. So you can check for this author. It's yeah. So in this particular book, you have a lot of Matlab examples as well to demonstrate what is happening in constraint optimization problem and so on. So this is one book, and there are other standard books like by Leuenberger and so on. Leuenberger. And another standard book is by Nosedal and Wright. Nosedal and Wright is another standard reference which most of the people working in optimization refer to. It has a lot of theorems and proofs related to. So the name of this textbook is Numerical Optimization. So Amir Beck is the book that I suggest for those who are new to the world of optimization. And these two books are little more mathematical. So once you are thorough with the basics, you can refer to these books for further understanding.
Thank you.
Okay, thank you. Any other questions? Chat box. Yeah. So there is a suggestion from Soumya to continue with penalty. So those who want to, the feedback form is supplied. So so how many would like to hear about a penalty? I'll wind up in another 5 minutes. Just raise your hands so that I can see, get a number, and others can leave in between. Okay, at least 2 are there. So those who want to continue can continue. Others are free to leave. We will have the next session at yeah. So please circulate the feedback form, and we will have the next session at 2:30 in the afternoon, and that will be from outside India. So please try to make it to that session, and it will be about smart grids in Europe. So he will give an overall picture of what are the smart grid projects that are happening in Europe. So please try to make it to that session, and there it is an odd time, but still he will be joining for the session. So please try to make it at 2:30 in the afternoon. Okay, so I'll quickly continue with the penalty function. Okay, so what is happening with the penalty function method is it is actually an algorithm. It is an algorithm to solve constrained optimization problem. It is an algorithm to solve constrained optimization problem. And the method is that you will try to convert the constrained optimization problem into an unconstrained optimization problem, and you will try to solve a sequence of such unconstrained optimization problem to get to the solution of constrained optimization problem. So I'll tell it slowly. So there are basically 2 or 3 steps happening. So the thing happening is, first thing what you will do is you will try to convert the constraints. So the constraints are posing as the difficulty. So we'll convert the constraints or constrained optimization problem to an unconstrained optimization problem using penalty function. So we'll see what is a penalty function. So using a penalty function, and once we have the unconstrained optimization problem with the penalty function, we'll solve a sequence. So this is important. A sequence of such unconstrained optimization problem constraint optimization problem to find the solution of constraint optimization problem. Okay, so this is what is happening in penalty function method. Even this is what is happening in something called as barrier function method, and there is another method called as augmented Lagrangian. So this is very powerful method. So I'll just mention the name here, augmented Lagrangian method. So in another method is barrier function method. So in all these methods, this is what is happening. We are trying to convert the optimization problem, the constraint optimization, to an unconstrained optimization problem, either using a penalty function in penalty function method, or using something called as barrier function in barrier function method, or using a particular function called as augmented Lagrangian function in the case of augmented Lagrangian algorithm. And then we will solve the sequence of such unconstrained optimization problem to find the solution of constraint optimization problem. So now we'll limit our discussion to penalty function. So what is a penalty function? So a penalty function is any function which satisfies three properties. So a penalty function is any function, so I'll write it as p of x. It is any function which satisfies three properties. So there are three properties to be satisfied for a penalty function. So the first property is that p of x must be a continuous function. It cannot be a discontinuous function. It must be a continuous function. Second property is p of x cannot be negative. It need to be greater than or equal to 0 for all x in the entire space. Not restricting to the constraints, but in the entire space it need to be non-negative. And third condition is the critical one. Third condition says that this penalty function need to be equal to 0 if and only if x belongs to capital X. So this capital X is actually defining the constraint space or constrained set, right? If an x belongs to this constraint set, then this penalty function must take the value 0. Okay, and otherwise it need to be greater than or equal to 0. If the x is outside the constraint set, it need to be it can be greater than or equal to 0. So this the penalty function cannot take the value negative. It can only take non-negative. It can take 0 or positive. It is 0 if this x belongs to the constraint set, and it can be positive if x is not belonging to the constraint set. So if any function which satisfies these three properties, then that function can be called as a penalty function. One of the most popular penalty function that we generally use is actually the quadratic penalty function. Quadratic penalty function. So I'll just quickly write what is quadratic penalty function. So there are other penalty functions as well. For example, exact penalty function is there. Then logarithmic penalty function is there. So there are different penalty functions. So any functions which satisfy these three properties can be a penalty function. One most popular is quadratic penalty function. In the case of quadratic penalty function, it will have a form something like this. So we need so EI represents the equality constraints. So since it is quadratic, EI square. So summation I is equal to 1 to m. So all equality constraints, since it is quadratic, we have we include an half as well. So half summation I is equal to 1 to m EI square. So this is just considering the equality constraint, and you can see that these three conditions are satisfied. It is a continuous function. It is always greater than or equal to 0 because of the quadratic nature, and it is 0. Yeah, this is important. It is 0 if x belongs to capital X. Why? If x belongs to capital X, that means that ei of x equal to 0. Because of that, this will become 0. Okay, so this is one term. Now, in order to consider the inequality constraints, we'll consider the second term. So the second term goes something like this: half summation j is equal to 1 to L, the number of inequality constraints, and maximization maximum of 0 comma hj of x. I'll explain this in a minute, the whole square. So this second term, this term will take care of the inequality constraints, and this is also satisfying these three properties. You can verify that this is a continuous function. This will be always greater than or equal to 0 because of this square term, and this is something you need to understand. Why this is equal to 0? Why the second term is equal to 0 if the inequality constraint is satisfied? What is inequality constraint? Inequality constraint says that hj of x need to be less than or equal to 0. So if some x satisfies or if some x belongs to this capital X, then hj of x will be less than or equal to 0. Okay, so that means that will be less than or equal to 0. So if x belongs to this capital X, what it means is this will be less than or equal to 0. So this will be less than or equal to 0 if x belongs to capital X, right? So if this is less than or equal to 0, maximum of 0 and this term will always be 0, right? Because this will be less than or equal to 0, so maximum of 0 and hj of x will be 0, and hence this condition is satisfied if x belongs to the constraint set, or x satisfies the inequality constraint. Okay, so this is a potential penalty function which satisfies these three properties. Now, what is the unconstrained optimization problem? So as I said, we have the constraint optimization problem need to be converted into an unconstrained optimization problem using the penalty function p of x. P of x can be any penalty function. Here we consider the quadratic penalty function, and now we will need to solve the unconstrained optimization. So what is the unconstrained optimization problem? So the unconstrained optimization problem is given by f of x, which is the objective function of the constrained optimization problem, plus a parameter ck times p of x. So p of x is the penalty function. Ck is a new parameter that I have added. So this is a scalar. So this belongs to R. And so this is the new objective function. Since it is an unconstrained optimization problem, there are no constraints. So this is minimized with respect to x. And so this is the unconstrained optimization problem that I need to solve. This is the unconstrained optimization problem that I need to solve. And suppose if I solve this problem, and if I take argument of this, and with this particular ck, so I'll tell about ck. So with the ck, suppose the solution to this is xk. Okay, suppose I have put a ck which can be any scalar. Okay, it can be 1, 2, or some scalar, and suppose I got the solution to this as xk. Now I need to solve a sequence of such optimization problem. Now, how to obtain the sequence of such optimization problem? In order to define a sequence of such optimization problem, I need to take the ck as a sequence. So this ck is a sequence which goes to infinity. Okay, so it can be 1, 2, 3, 4, etc., or any sequence which takes to infinity. If you take this as a sequence which goes to infinity, then the theorem says that xk will converge to x star, which is the solution of the primal of the constrained optimization problem, as ck converges to infinity. Okay, so this is the result. So this result is being used in penalty function algorithm. Okay, so we have the constraint optimization problem. We will construct the unconstrained optimization problem using the parameter ck with the help of penalty function p of x, and we will solve the optimization problem to obtain xk. and we will consider the sequence which converges to infinity. So practically we cannot consider a sequence which converges to infinity, but while doing algorithm we can consider a sequence which converges to a high value. As the sequence ck converges to a high value, the sequence of these solutions will converge almost near to the solution of this x star. Okay, so this is what is happening in penalty function algorithm. Similar thing is happening in the case of barrier function. In place of penalty function you have barrier function, and in the case of augmented Lagrangian you have something called as augmented Lagrangian function. Okay, so I hope you got a brief idea of penalty function method as well. Any other questions? Is that clear, the idea behind penalty function? So this is a very powerful technique. This is very much used to find constrained optimization problem. So either the constraint optimization problem can be solved as a dual problem. Sometimes the dual, in order to find the solution of dual problem in algorithms, we use one of these methods, penalty function or barrier function or augmented Lagrangian and so on. Okay, so any more questions? So shall I start?
Sir, penalty function always continues.
Sorry, Sharath, I cannot hear you properly. Can you repeat?
Sir,
no, it's not clear. Maybe can you type in the chat box, or maybe you can get to me directly in phone as well if you have my number. I'm not getting the question.
Now I'm.
Okay, so if there are no more questions, we'll stop the session and we'll continue with the next session at 2:30 in the afternoon. So thank you very much for joining, and thank you for giving me this opportunity. Thank you.